So we've seen in the PhET simulation how we can't predict exactly where a particle is going to hit the screen in one of those interference experiments. Like everything quantum mechanical, it's an inherently probabilistic phenomenon. So we need a way to describe these two things, right? We need to describe how particles have some wave-like behavior and how there can be spatially varying probability for detecting a particle. So let's start by thinking a little bit about particles and waves in classical physics, and then compare that to what's different in quantum physics. So let's split up the board here. Okay, I'll grab another color. So classically for particles, so this is thinking back to what you talked about in Physics 117. Right, the point of classical mechanics is in general to calculate the position of a particle as a function of time. So your goal is to, it's described by, let's keep it one-dimensional, x of t, the trajectory of our particle. Now, classically, particles and waves are just completely different things, right? So for waves, so you learned about classical waves in Physics 217, and you learned how you can describe mathematically a wave in the following way. So you describe by giving the displacement as a function of both position and time. I think Knight used d of x and t for a general wave displacement. I actually kind of like that notation. So a few things, right? So d of x of t for a classical wave is real. Or if, like we talked about at the beginning of Townsend, if we want to use complex exponentials to describe a sinusoidal classical wave, even if we sort of use complex numbers as a mathematical convenience, the physically meaningful part of the wave really is a real quantity. And then moreover, this displacement is what I'll call physically tangible. So, for example, right, you might think about, so if you have a wave on a one-dimensional string, right, this displacement describes how far the string is displaced from equilibrium. Or if we're talking about sound, right, this d might represent a pressure that varies in both position and time. So what gets interesting is to think about how different everything is in quantum physics. So quantum. So it turns out that particles and waves are really united in quantum mechanics, that particles have wave-like properties. And as you saw in the reading, we describe particles using the wave function by the wave function is traditionally denoted with a Greek capital psi. And I'll write capital psi like so. I'll write it as a function of position and time. For now, we're going to just work in one dimension. And so I'd write this as psi of xt. If this were 3D, I'd have additional dependence on other spatial coordinates. So this is psi. Okay. So one really big difference between classical and quantum waves is that, in general, psi of x and t is complex. This won't entirely, we won't see exactly how that's so for a little bit, but it turns out that you really do need the entire complex psi to be physically meaningful. You can't just isolate the real part the way you can for a classical wave. The other thing is thinking about what's physically meaningful here. Right? So the wave function itself turns out to be not quite the thing that is physically meaningful. What's meaningful is the following. So psi star psi. So as usual, the star here means complex conjugate, right? And the cleaner way to write this is, I'll just write this as psi modulus squared is what's physically meaningful. And this is where the probability comes in. So we, in particular, think about psi modulus squared as what we call a probability density. So let me be specific about that. Now, specifically, right, what psi modulus squared dx means is it's the probability density for finding a particle between x and x plus dx at some time t. Okay, so what the heck does this mean? So I'm gonna need to erase this. So this was the board that used to be in my office, and it's smaller, obviously, than the boards in our classroom. So I apologize for having to erase a little more often. So let's see what we mean by this. So the best way for me that I think is helpful for thinking about probability density is to use an analogy to something we might be more familiar with. Now, in Physics 118, you might have talked about linear charge density, right? When you were, say, thinking about calculating the electric field of some line of charge. But just because 118 was probably a while ago, and let's try to stick with the most sort of concrete analogy we can. I'm gonna think about linear mass density. So analogy and let me call that, I'll just call it lambda of x. I know lambda is not wavelength here, but oftentimes people use lambda for linear densities. So what I mean by the following is this. So suppose I have some rope, and that it's a funny rope that doesn't have a constant thickness. So maybe this rope starts off like so, but then it gets a little bit wider. And it sort of has this wider section, and then maybe it gets really skinny. Like so. And then it maybe widens up again. Something like that. Let me just fill this in. This is so. If we assume that our rope is made of the same material throughout, right, then I can think of its linear mass density as sort of the mass per unit length. And if I graph that, it might look something like this. So if I have x here, and I have my linear mass density. So so it starts off sort of in the middle here, and it's like this. I'm drawing a little crooked, forgive me. Starts off sort of constant here, but then it increases, right? So let's say it increases and then sort of stays flat for a while, sort of in this sort of middle section, and then it drops again. So maybe it drops to over here, and in this narrow bit it has a small density, and then it kind of goes back up. Again, something like this, right? So if I wanted to find the mass of a certain amount of string between 2 points, so let me just call this x0 and x1, I do the following. So the mass of string that would be given by the integral of this linear mass density from x0 to x1, the integral of lambda of x dx. Right? So, moreover, the total length of the mass of the string would be given by the integral of this linear mass density over the entire string. So, or it's a rope, sorry. So instead of writing symbols for this, I'll just write entire rope. Dx. Now, the wave function and the probability density in quantum physics works in a really similar way. So in quantum mechanics, I can similarly draw a graph of the probability density psi star psi as a function of position. Maybe it looks something like this. Here's x, here's I'll plot psi x t modulus squared right there. Okay, and let's suppose that it looks something like this time. So now the probability of finding a particle. So if this wave function describes some particle, the probability of finding my particle between x0 and x1 is going to be given by the following. So prob of finding particle between x0 and x1, that's going to be equal to the integral of my probability density. So integral from x0 to x1 of this psi of x t modulus squared dx. Right? And I My dx is really important here. Similarly, we know that if we have a particle, it's got to be somewhere. So that's the requirement that and we know, so if the particle really exists, then the total probability of finding it somewhere in all of space has to be equal to 1. And in that case, what must be the case is that 1 has got to be equal to the integral of that probability density from minus infinity to positive infinity and this is what we call normalization. Normalization. So we'll look at an example of doing this in practice probably next time. But the idea, right, is that there's got the total integral, the probability density over all space has to be equal to 1 in order for that to be physically meaningful. Okay, so at this point, what I'd like you to do is to think about a clicker question, and then when we come back, we'll discuss the question.